A lot of people in education tend to disfavor memorization, but I think memorizing a lot of information is a great way to provide yourself with a foundation for future thought and future understanding, and seeing how values relate to each other is almost impossible unless you have the values, and it's much easier for me to work with information that's in my head rather than information that's scattered around the universe. So if I'm trying to understand acidity, then it's really useful for me to build sort of a representative table of compounds with their pKa's, and then build in other important information like the Lewis structure of the conjugate base, so I understand the acid-base relationship. And it was through memorizing a bunch of pKa's and information about representative acids that my understanding of acidity really grew. So I can talk abstractly about acids all I want, but until I have actual values and organize those actual values in a reasonable way, I don't think I really understand acidity, what causes it, or any of those factors. So what I recommend to any organic chemistry student who's trying to get a handle on acidity and types of reactions and how acid-base reactions go is to gather a group of about 25 or 30 really simple common molecules and look at their pKa values and try to understand the relationship between groups of those compounds. And that's what I call my official pKa table for Chem 230. And if you've seen my videos on acidity and the factors that affect acidity, you'll know a lot of these already, so that would be a really helpful start. So let me go ahead, and I'm going to, because of the limitations of space here, normally I would do this on a big old whiteboard and I'd have plenty of space, but because I'm limited to this piece of paper, I'm just going to do some representative examples. I also like to organize things graphically, so I'm very much a visual learner. And so I'll put the strongest acids on one side of the paper, and that'll mean that their conjugates will be the weakest bases. So remember this inverse relationship between acids and bases, that if we know what the strongest acid is, and we don't have quite everything on the screen there, so let's give me a little more distance. Very amateurish here, but that's okay. Let's see if I can get, nope, not yet. Yes, you get to waste a minute of your time watching me try to get the whole friggin' paper on the screen. Alright, there we go, and we get some background stuff too, a little periodic table over here. Alright, so back to the content. Strongest acid might very well be HI, hydroiodic acid, which has a pKa of -9. And I should probably draw out more of the dot structure here, but again, I'm going to be very limited in space. So I'm going to put HI and I- as its conjugate. So let's put that conjugate down more at the bottom of the page. I- as being one of the very weakest bases. And the reason I'm starting with HI is because it's part of a very important series for me that demonstrate the size effects of the atom directly attached to hydrogen. So as we go from the very large iodine to the very small fluorine, you are going to decrease the acidity. And especially the difference in size between row 3 in the periodic table and row 2 in the periodic table is substantial. So that's got a huge effect on the acidity of HF versus HCl. HCl being one of our strong acids, HF being one of our very weak acids. And likewise, we can put these conjugate bases in order, where this fluoride tends to be a much stronger base than chloride, bromide, and iodide. So I think of these three as a set, and the one in the second row being a little different. And the thing that this series shows us is the effect of size of the atom attached to hydrogen and how it affects acidity. Right, and then I can go and use this as a starting point, HF at 3.2, and now we can change, without changing the size of the atom attached to hydrogen too much, we can change the electronegativity of the atom directly attached to hydrogen. And so HF at 3.2, water at about 16, ammonia at about 35, and methane about 50. Now we're showing that if you keep the size of the atom attached to hydrogen approximately the same, but change the electronegativity, you can very much change the acidity of the compound. So carbon attached to hydrogen, very nonpolar bond. The H is not very much a donatable H+, so you get a pKa of 50. HF, much more acidic because of the electronegativity of the HF. So here we see a trend where the electronegativity varies when the size doesn't, and that very strongly affects the pKa. And so I would expect that if you're trying to figure out a pKa of a compound, you might see how it compares to water. So something like methanol, CH3OH, very much compares to water because it's basically an OH group with something that won't affect the pKa or the acidity very much attached to it. So a hydrogen versus a methyl is not big of a change. So HOH versus CH3OH, you're going to expect very similar pKa's. So that's where memorizing simple representative compounds and then seeing the comparison to other compounds allows us to predict pKa's. Alright, and so what's another thing? Hybridization is another thing that affects the pKa. So to show that, I can show CH3CH3, ethane being structurally very similar to methane, nonpolar CH bonds, pK about the same. And then if I change the hybridization and do ethylene or ethene, we drop the pK to 44, but then if we go to ethine or acetylene, we have pK of 25. So depending on the hybridization of the carbon attached to hydrogen or other elements, so if you've got an oxygen attached to a hydrogen, then its hybridization is going to affect how well it attaches to that. So with other elements, hybridization is also important, but ethane versus ethene versus ethine, very big pKa change based on the change in the hybridization of the carbon that's attached to the hydrogen. So anytime you see an acetylene or acetylide with something other than hydrogen here, there's a starting point for understanding its pKa and thus its acidity. So these are all factors or properties of the element directly attached to hydrogen and how they would affect the pKa of a compound. And you can see that we've got a bunch of very small representative molecules with really different features, which will be our starting point for understanding other compounds that might be similar. Alright, so after hybridization, we could put in resonance. So if we have something with all single bonds and no resonance forms, like methanol or water, pK is about 16. If you go with putting a classic conjugated system next to the alcohol, so phenol is phenyl alcohol, and the pK would then be 10, so you can see how much more acidic the resonance and the electron delocalization will be, and then much more powerful electron delocalization would be acetic acid, where the negative charge can be split between two oxygens, and then you have pKa 4.74. So as you have more electron delocalization or resonance, then some representative compounds to show the amount of different electron delocalization or resonance that's there. Then you're going to have inductive effects. And for something like that, I would compare acetic acid, 4.74, to trifluoroacetic acid, where the fluorines remote in the molecule will be pulling electron density away from the hydrogen, making it more acidic. So I think this one's about 0. It's either 0.3 or minus 0.3, I don't remember exactly, but it's about 0 because those extra fluorines in the molecule. And then the other last effect that I would put in there is charge. And again, if I'm going to put those to scale, go a little lower on the page, and you might want just another page to put the conjugate bases on, but if I want to look at charge effects, I'm going to have a negative compound, or ion, negative ion, this pKa about 42, compared to a neutral, pKa about 16, compared to a positively charged ion with pKa minus 1.7. So very strong acid, fairly neutral, very, very weak acid, and actually a fairly strong base as we change the charge. And then once I have this starting point, I can see now how changing the charge on something will dramatically make something more acidic if we go to more positive charge, or more basic if we go to negative charge. And as we compare other pairs of compounds, we can see a similar effect. That the more anionic something is, the less acidic or more basic it might be, and the more cationic something is, the more acidic it is, and the less basic. So that's something that I think is going to be really important for me, is as I start to try to understand acidity, I want to memorize the pKa's of a bunch of different molecules, and then the comparisons becomes fairly easy. So if I start to look at something like NH3 versus NH4+, I can see that the big difference between these two, especially if I look at the dot structure and see that in each case a hydrogen is attached to an sp3 nitrogen, right? So there's no hybridization effects, there's no size effects, there's no electronegativity effects. There's no electronegative element in there to give inductive effects. There's no double bond for resonance effects, but the charge is different. This is neutral, and that's positive. So I might say, okay, so what's the pKa of this one? And I say, well, how much does the charge affect the acidity of a molecular ion? If I have water, right, water is pKa about 16. If I go to H3O+, I go to about -2, so I'm going to go 18 units this way, and I'll certainly get the direction right, even though the magnitude might not be perfect. Ammonia is about pKa 35, and so if I take 18 units off of that, I get a prediction that pKa is 17. Now really it's 10, right? pKa is 10 is actual, and pKa is 17 is my prediction based on how much I think the charge would affect the pKa. And certainly these two aren't equal, but I've got a pretty decent estimate that ammonium is going to be quite a bit more acidic than ammonia, just like hydronium is quite a bit more acidic than water. And because oxygen and nitrogen affect the compounds and ions differently, it's not going to be a perfect comparison, but it's going to get us in the ballpark for sure. So if I know a bunch of pKa's and how the structure of the molecular ion is important in determining and understanding the pKa, then I can start to understand compounds I've never thought of before, or ions I've never thought of before, by comparison to things I know, given the basic principles, factors that affect acidity. So again, I have size, electronegativity, hybridization, resonance, or electron delocalization, inductive effects, and charge as my 6 factors I think about when I'm trying to understand and predict acidity of different compounds. And the more values you study and the more values you know, the easier it is to reason along these lines. So for my students, memorizing all of the molecules and ions on this page and their respective pKa's is really important, and I'd expect you to have that down by the next test. And then being able to make reasonable predictions of new molecules is something that this would enable you to do if you understand what I'm talking about here. And if not, always feel free to message me and I will try to straighten out whatever I can.